Hi, I'm Colin. In this module, we're going to analyze the rational function f of x equals x squared minus 1 all over x minus 1, which has a point of discontinuity at x equals 1. By analyzing this point using limits, we will show how we can make the function continuous by extending its domain to include this point. Firstly, recall that the quotient of one polynomial over another is called a rational function. Here we have the quotient of a quadratic polynomial, x squared minus 1, over a linear polynomial, x minus 1. It looks like a fairly complicated function, and chances are, at this point, you probably have very little idea of what its graph looks like, or how we can even sketch it. But that's okay. Let's start with what we do know, just by looking at the formula. Firstly, note that the domain of the function will be all the real numbers such that the denominator is not 0. That means the domain will be all the real numbers, but we must remove x equals 1. So, written in set notation, the domain is therefore the set of all real numbers R such that x is not equal to 1. Now, this set turns out to be the union of two disjoint intervals, so we may write this set in interval notation too. We have all the real numbers below 1, not including 1, and all the real numbers above 1, not including 1. And since we want to consider them together, we take their union. In this unit, you must be familiar with how to write sets in set notation, and when these sets happen to be intervals, in interval notation too. We note that here, we can write the set in a third but very elegant way. That is, the set of all the real numbers minus the number 1. In other words, the set of all the real numbers, but with the single element 1 removed from this set. At this stage, we still have very little clue what this function looks like graphically. But having worked out the domain, we do know that if we try to draw the curve, one thing is certain. We will have to lift the pen off the page when we hit x equals 1, since the function isn't defined there. Hypothetically, that means the function could have a vertical asymptote at x equals 1. An asymptote is a line to which the curve of the function approaches closer and closer but never actually reaches. It could also mean that the function makes some sort of a jump at x equals 1. Or it could mean that the curve has a hole at x equals 1. All of these are possibilities, and in any case, it means the function is what we call discontinuous at x equals 1. In contrast, a function that is continuous is one where we can draw its graph all in one go without having to lift the pen off the page at any point. Before we sketch the graph, let's try and investigate the discontinuity at x equals 1. As tempting as it may be, we're not allowed to write f of 1, because 1 is not part of the domain, and so the function is not defined there. This means the best that we can hope for is to study how the function behaves very, very close to x equals 1, and this is where the concept of limits can help us. Limits are often used to investigate how a function behaves close to a point without having to be at the problematic point itself. Okay, so what we are first going to do is see how the function behaves as we slowly approach x equals 1 from the left. For example, let's pick x to be 0.9 and work out what the y value is at x equals 0.9. Substituting it into our function, and then evaluating in your calculator, you'll discover that the y value is 1.9. Now, edging even closer to x equals 1, by picking x to be 0.99, you can check that the y value is 1.99. Now, edging even closer by picking x to be 0.999, which is incredibly close to x equals 1, you can check that the y value is 1.999. There seems to be a pattern to this. We can observe the following. As x approaches 1 from the left, f of x approaches 2. Now, mathematically, we articulate this by saying that the limit of the function as x approaches 1 from the left is equal to 2. Note that the concept of approaching x equals 1 from the left is denoted by this negative sign here. And this limit is an example of what's called the left-sided limit. Okay, so we know that as we approach closer and closer to x equals 1 from the left, the curve approaches the y value too. Let's do a similar calculation, where we now approach x equals 1 from the right side. For example, let's pick x to be 1.1 and work out what the y value is at x equals 1.1. Substituting it into our function, and evaluating in your calculator, you'll discover that the y value is 2.1. Now, edging even closer to x equals 1 by picking x to be 1.01, you can check that the y value is 2.01. Now, edging even closer by picking x to be 1.001, which is incredibly close to x equals 1, you can check that the y value is 2.001. Here, we can observe that as x approaches 1 from the right, f of x approaches 2. And mathematically, we say that the limits of the function f of x as x approaches 1 from the right is 2. The concept of approaching x equals 1 from the right is denoted by this positive sign here. And this limit is an example of what we call the right-sided limit. And finally, since the left and right-sided limits are the same number, here that's 2, we say that the limit exists. And we write it as the following. Where there is no longer a need for a plus-minus sign to indicate the direction of approach. That's because as we approach closer and closer to x equals 1 from either direction, left or right, the curve approaches the same y value, that's 2. Now, this calculation actually shows that the type of discontinuity at x equals 1 must be a hole. If the discontinuity was a jump instead, then the left and right limits will be different numbers, representing the fact that the curve approaches different y values depending on the direction of approach. And if the discontinuity was a vertical asymptote, then the function will be approaching either infinity or minus infinity, as x edges closer to 1, which is not the case here, since we know that the function is approaching a finite number, that is, 2. Okay, let's now sketch the curve of our function, which we now know to have a hole at x equals 1. We will then show you how this hole can effectively be plugged up using the limit we just calculated. To help sketch the function, I'm going to employ a little algebraic trickery to make this formula here look simpler than it currently appears. Firstly, observe that the numerator can be thought of as x squared minus 1 squared. That is, the difference of two squares. Thus, we can factorize the numerator as x minus 1 times x plus 1. The linear factor x minus 1 in both top and bottom can then cancel, leaving us with just x plus 1. Also bear in mind that x isn't allowed to be 1, since that's not part of the domain. Since x plus 1 is linear, the graph of our original function is therefore just the straight line with y-intercept 1 and slope 1, where x is not allowed to be 1. That is, the 45 degrees diagonal line through the y-axis at 1. That has a hole at x equals 1. Having now drawn the graph, we can observe that the only reason that the function is not continuous is because of this single hole. Therefore, a simple solution to make the function continuous is to just plug in the hole, so to speak. Specifically, we are going to define the y value of this function at x equals 1, which is currently undefined, to be the y value of this hole, which we found earlier by calculating the limit of the function as x approached 1, which turned out to be 2. In summary, we've effectively extended the domain of the original function to include the x value 1. Moreover, by defining the y value to be 2 here, we've plugged up the hole, thereby making the original function continuous everywhere, which would allow us to sketch its curve in one continuous smooth action without having to lift the pen off the page. The formula for this extended function, which now has domain all the real numbers, can be written as the following. For x values not equal to 1, the function is given by the original formula, x squared minus 1 all over x minus 1. This simply describes the original function we started with. And when x is equal to 1, the function value is just 2. This technique of making a discontinuous function continuous by filling in the holes is an important and general technique in theoretical mathematics. In fact, such holes are formally known as removable singularities. With the word removable precisely implying that these discontinuities can be removed or plugged in by setting the y value of the hole to be the limit of the function as you approach the hole. Alright, I hope you found that useful. See you next time.